Hi guys, this is A2 Chemistry, Analytical Chemistry, and we are looking at combined techniques. Question 1. Draw the structure of the dipeptide GLY-SER showing the peptide bond in full. So GLY-SER stands for glycine serine. So we need to make a dipeptide. So we start with the NH2 group of glycine followed by carbon with two hydrogen atoms attached to it, followed by a C double bond O group, which is bonded to the NH group of serine next to carbon with one hydrogen and one CH2OH group as the R group, and it ends with the COOH group. Now, the CONH in between these two amino acid residues is the peptide bond. And this is the structure of the dipeptide GLY-SER. The infrared spectrum of GLY-SER is shown below. Use the data booklet to identify the bond in the molecule GLY-SER that is responsible for each of the peaks indicated on the above infrared spectrum. So E, F, and G. E is a peak that is in the region beyond 3000 wave numbers. So this should correspond to either the OH group of the alcohol or the NH group of the amine. So it can correspond to both of these. So we will write OH or NH2 because both of them lie in the same region. And next we have F. F lies in the region of between 1600 and 1700. So this corresponds to a C double bond O group, which will have a peak in this region. And G is close to 1100 or between 1000 to 1100 wave numbers. This corresponds to a C single bond O group, which is the only group that has a peak in the region below 1500 wave numbers that can be identified. Question 2. Compound F contains the elements carbon, hydrogen, and oxygen only. All carbon-carbon bonds in F are single bonds. The structure of F was analyzed by mass spectrometry and infrared and NMR spectroscopy. The mass spectrum shows that the ME value of the M peak is 90, which means the MR of this compound is 90. The ratio of the heights of the M and M plus 1 peaks is 22.1 is to 0.7. Use the ratio of the heights of the M and M plus 1 peaks to calculate the number of carbon atoms in a molecule of F. So this would be N equals 100 upon 1.1 into height of M plus 1 upon height of M. So 100 upon 1.1 multiplied by 0.7 upon 22.1. This gives us a value of 2.88, which will be rounded up to 3 because carbon atoms are in whole numbers. So we have 3 carbon atoms present in our molecule. So number of carbon atoms is 3. Suggest the molecular formula of F. So the MR is 90. Carbon atoms are 3, which is 36. 12 3 is 36. So 90 minus 36 is 54. So out of 54, if we have 3 carbon atoms, the maximum number of hydrogen that can be attached to 3 carbon atoms would be Cn H2n plus 2. So that would be, if n is 3, this would be 3 into 2, which is 6, plus 2, which is 8. So max number of hydrogen atoms can be 8. So working about this, if we remove one oxygen from 54, 54 minus 16, we are left with 16, 38, and 38 hydrogens are not possible. So out of 38, if we remove another oxygen, we're left with 22. the maximum number of hydrogen we can have is 8. So that is also not possible. So if we remove another oxygen from 22, we're left with 6, which is less than 8, which is very much possible. So we end up with 3 carbon, 6 hydrogen, and 3 oxygen because we remove 3 oxygen. So the molecular formula of our compound F would be C3H6O3. The infrared spectrum of F was obtained. Use the data booklet and your knowledge of infrared spectroscopy to identify the type of bond and the functional group responsible for these three absorptions. So, an absorption at 3350 is broad and strong. The type of bond would be the OH bond, and the functional group would be an alcohol. At 2680, very broad and strong is due to another OH group, but this time this OH group is part of the carboxylic group, carboxylic acid. At 1725, we have a strong peak corresponding to C double bond O, and since the carboxylic acid group has already been identified in the absorption at 2680, so this C double bond O also belongs to that same carboxylic acid group. F was dissolved in deuterated trichloromethane CdCl3, and the proton NMR spectrum of this solution obtained. Use the data booklet and your answers to A2, which is the molecular formula C3H6O3, to complete the table 1 for the proton NMR spectrum of F. The actual chemical shift for the 4 absorptions in F has been added for you. So since we have C3H6O3, it means that if there are 4 absorptions, 3 of them would belong to protons attached to carbon, and one of them would be a proton attached to an oxygen atom, so an OH group. So a singlet in the range of 0.5 to 6.0 should be the OH group, which is this one. The peak at the extreme right, close to 13, is a very specific peak for the COH group. So our compound has an OH group and a COH group. Then we have a peak that is a doublet in the range of 0.9 to 1.7. So this belongs to a group which is next to a CH group. And then we've got a peak at close to 4, splitting into 4. So that is of an environment next to a CH3 group, and the same environment is also attached to an oxygen atom, and attached to an oxygen atom means that it is next to the OH. So this belongs to the quartet peak belongs to the CH group, which means the CHC groups next to CH is the reason for the doublet. So we have identified all groups. So assembling the structure together, now we are left with COOH. So the central carbon atom gets the COOH attached to it, and this is the compound that we have. So the compound is 1,2,3,2 hydroxy propanoic acid. So the peak at 1.4 corresponds to a CH3 group next to an alkyl group, and the relative peak area refers to number of protons present. So the relative peak area would be 3. For 3.9, the peak belongs to a CH group next to an oxygen atom. So the relative peak area here, since there is only one proton present, is 1. Then we have a peak at 4.7 corresponding to the alcohol OH group. The peak area would be 1 again, and the peak at the extreme end at 12.9 belongs to the RCOOH proton, again having a single relative peak area. So in this way, we have identified all 4 absorptions corresponding to which part of 2-hydroxypropanoic acid they belong to? Describe and explain the splitting pattern for the absorption at chemical shift of 1.4. It is a doublet due to the presence of a single proton in its adjacent chemical environment. F was dissolved in D2O and the proton NMR spectrum of this new solution obtained. Two of the absorptions in table 1 were not present in this spectrum. Which absorptions were not present? So absorptions at 4.7 belonging to the alcohol group and the absorption at 12.9 belonging to the carboxylic group disappeared on addition of D2O. Suggest a structure of F. F is CH3, CHOH, and COOH. And the name of this compound is 2-hydroxypropanoic acid. Question 3. Compound F is a carboxylic acid. Compound F contains 31.4% oxygen by mass and its mass spectrum has a molecular and peak at Me equals 102. So 102 is the MR of compound F. Use all this information to show that the molecular formula of compound F is C5H10O2 to all your working. So the number of oxygen atoms can be obtained by using the percentage of oxygen. So 31.4 upon 100 into 102 gives us a mass number of 32, which means two oxygen atoms are present. So out of the total mass 102, if we minus 32, we have a mass number of 70 remaining. So now the next step would be to subtract the mass of COOH. So MR of COOH would be 12 plus 32 plus 1. So this is 45. So out of a total of 102, if we subtract 45, we are left with a mass of 57. So the mass of carbon plus hydrogen should be equal to 70 and the mass of the compound without the COOH group should be 57. So if we have 12 for one carbon, 12 makes it 24, 12 makes it 36, and 12 makes it 48, and another 12 would make it 60. So if we have four carbon atoms, so the mass comes to 48. 57 minus 48 gives us 9 hydrogen atoms. So this concludes that the formula could be C4H9 for the remaining part of the compound. And doing the same calculation for C and H, so if we got 70 as the mass of carbon and hydrogen, so that would be 12, 24, 36, 48, and 60. And we minus 60 from 70, we end up with a value of C5H10 for hydrogen because there are 12, sorry, not 12, there are 5 carbon atoms present, each having a mass of 12. So C5H10 and we get O2 this way, and in the other case we get C4H9 COOH, which also comes to C5H10 and O2. So in both ways we ended up with the molecular formula of C5H10O2. There are four possible structural isomers of C5H10O2 that are carboxylic acids. The first isomer has been drawn. Draw the skeletal formula of three other structural isomers. So, if we look at this structure, we can actually shift the substrate group. This is the substrate group CH3 from the second position to the third position on the straight chain. So, we can have this is the skeletal formula of the straight chain part of the molecule. And if we shift the CH3 to this carbon atom, we have got another molecule. What we can do is we can have a straight chain for the entire carboxylic acid. So 1, 2, 3, 4, 5. We can have a double bond O here and a single bond OH here. So this is the third isomer, and the fourth isomer could be we can have a C double bond O present here with an OH. So this is 1, this is 2, and this is 3. We can have three CH3 groups attached to the same carbon atom that is attached to the COOH group, making the fourth isomer of the required carboxylic acid. State the systematic name of isomer 1. So the systematic name of isomer 1 would be 1, 2, 3, and 4. So it would be 2-methyl butanoic acid. F is one of the four structural isomers in B1. A carbon 30 NMR spectrum of F is shown. Use the spectrum to identify isomer F. Draw its structure in the box below. So what we have is three environments present for carbon. So if you look at the structures of the carboxylic acids drawn, the only isomer with three absorptions that is possible would be the one with the three CH3 groups. So it would be C. We've got three CH3 groups and a COOH group. So using the data table for carbon 13 and NMR, this group would lie in the range of 160 to 185 parts per million. This would lie in the range of 0 to 50 parts per million, and the three CH3 groups 1, 2, and 3 would also lie in the range of 0 to 50 ppm. And since we've got a peak close to 25 and a peak close on 40, so these two peaks correspond to the two different environments, CH3 next to carbon and carbon between 3 CH3 and 1 C double bond O. And since the carbon is next to C double bond O, the peak at 40 looks like it is the carbon atom, single carbon atom next to C double bond O. The peak at between 20 and 30 is due to the three CH3 groups, and the peak close to 180 corresponds to the COOH group. So these are the three environments in the isomer selected, and the question says use the spectrum to identify isomer F and draw its structure in the box below. So the isomer would be in its skeletal form. This. Use the data booklet and your knowledge of carbon-13 NMR spectroscopy to identify the environment and hybridization of the carbon atom responsible for each of the three absorptions. So environment of the carbon atom would be CH3, and the hybridization of the carbon atom would be sp3, because there are four single bonds formed by each of the CH3 groups. And the peak at 41 would be a carbon attached to three CH3 groups and to a CO group next to it, and this would be the one that would have a hybridization of sp3 as well because it is forming four single bonds, and the peak at 179, which is the one we mentioned close to 180, would be the peak for the COOH group, and here the hybridization would be sp2 because the carbon atom is forming a double bond with one of the oxygen atoms, and a double bond consists of a sigma and pi. Presence of a single pi bond result in the hybridization being sp2 hybridized. G is another of the four structural isomers in B1. The proton NMR spectrum of G is shown. So here we've got a peak that is splitting into two that belongs to a CH3 group next to a CH group. Then we've got another peak that belongs to an environment that is next to multiple hydrogen atoms because it is a multiplet. So this will also be between various alkyl groups. Then we've got a peak that splits into two that is next to a CH, and it is also next to a C double bond O because of its chemical shift value being between 2.2 to 3.0. So this is attached to a C double bond O group, and we've got a peak at 11.5, which is a singlet, which is typical for a carboxylic acid. So this belongs to the COOH group. And since we've got one position left and no other environments present, so there should be another CH3 group attached to the CH group. So the first peak, the first doublet belongs to two CH3 groups. The multiplet belongs to the CH group. The doublet, which is between 2.2 and 3, belongs to a CH2 next to C double bond O. And this carboxylic acid is 1, 2, 3. In fact, the numbering begins with the carboxylic group. So we start with the COOH carbon being 1, 2, and 3. So the name of this compound is 2-methyl and 3 carbon acid is propanoic acid. Propanoic acid. So since we have identified our structure, now let's fill the table. The table asks the actual chemical shift for the four absorptions G and the splitting pattern at 1.6 has been added for you. So that splitting pattern was multiplied. So 0.9 is due to two CH3 groups. Number of protons is 6 in this case, and the split is a doublet. At 1.6, the proton is a CH bonded to three other groups, and it is next to a C double bond O, and that effect is not seen here. Wait a minute. If we have a CH3, if we have two C, then how can we have a CH2 next to CH? So we have not accounted for the peak at 2.224. That should belong to a CH2 next to the C double bond O. So the CH2 group is missing from in between here. So let's revisit the structure. We don't have the C double bond O group directly attached to the CH. We have a CH2 in between, because of which the multiplet lies in the range of 0.9 to 1.7. Then we've got a COOH group present next to the CH2 group, which changes the name of the carboxylic acid as well, because the straight chain carbon atoms are now four. So one, two, three, and four. So the name becomes 3 methyl and butanoic acid. So coming back to the table, so this is a CH group attached to three alkyl groups having one proton in it, which is a multiplet. And if we look at the number of splits that are possible, so the adjacent hydrogen atoms would be 3 plus 3 plus 2, 8, so 9 splits. The next peak at 2.4 belongs to the CH2 group next to the C double bond O group because of its position on the x-axis. And the CH2 group contains two hydrogen atoms or two protons, and the split that is visible is a doublet. And finally, the peak at 11.5 corresponds to the carboxylic acid group, which has a single proton in it. And since it is a functional group, the splitting is also a singlet. Deduce which isomer is G and draw its structure in the box. So schedule formula of G would be 1, 2, 3, 4, and another CH3 group here. Either we can draw it this way or even better this way. And then we've got a double bond O here and OH completing the structure. Name or give the formula of a suitable solvent for obtaining a proton NMR spectrum. So the solvent that we can use is either CCl4 in which there are no hydrogen atoms present, or we could use CdCl3 in which the proton has been replaced by a deuterium isotope of hydrogen.